Good evening, everybody. Welcome back to lecture number 3. Today we will continue our revision of basic power concepts. So last time we covered what? The value of lost load in different regions, and we notice it varies by the economy. I'm not going to ask you in every class what is the difference, but you have to get a sense of it, okay? So let's move to another continuation where we will talk about the three-phase systems. It's a revision for you to familiarize yourself with those problems before we go to the per-unit system. Okay? It's roughly around 60 slides. Usually, this is a revision from undergrad. This is based on the undergrad course, but it's worth mentioning it today. We have students who do not have knowledge of power system, so I feel it's worth giving them this lecture. So this lecture, I had to acknowledge Dr. Muhammad Khalid, who's his advisor, and Dr. Muhaini, who's his advisor, and Dr. Ma'ad, who's his advisor. So those slides were developed, and I'm presenting to you. So we want to review and understand basic concepts of a three-phase system. Are we going to review induction machines? No, synchronous. No. Synchronous, maybe. But for now, we're not going to cover all the electric energy undergrad course. Instead, what we will cover is basic concepts. So review, understand, and know how to do the power calculation. We need to know how to do the power calculation before we go to the per-unit system. Okay? So, this is how it looks like. How many transmission lines in this tower? Experienced guy. In this tower, how many transmission lines? Is it single or double?
Two.
No, for this tower, only this tower.
Two sets. One on the right side.
Good. So this is effectively one tower is having how many lines? Two lines. So this to save money, sometimes for big towers they put two transmission lines. Okay? They put a spacing distance between them to avoid magnetic coupling between them. You have to decouple them. There is a whole science for high voltage analysis, insulators, etc. It's covered in this course where they teach you what's the minimum distance between conductors. Not only that, they are smart. They put phase A, here they put phase B. And then here they put phase B, here they put maybe phase A. In the second layer, in the third layer maybe they put A and C. So that they minimize the electromagnetic coupling between the two transmission lines. It's in one tower, two transmission lines. We already covered that. This is a sample of voltage levels for a typical grid. This is what is this device? Transformer. So let me ask you a question. Who has experience drawing the 3D transformers, transmission lines, etc.? Do you have experience in that? If you work for mice, okay, and they ask you to generate a 3D cartoon-like. And this is an area of business where graphic designers go into power system. So it is official title in many companies. They have graphic designers or they have digital marketers to create those figures. Engineers don't know how to do these things. Okay? So most probably this was developed by maybe graphic designer. This is just for your own knowledge. Okay? Sometimes it's better it's worth using it. How many transformers we have here? 6. Each one is having primary, secondary, primary, secondary, primary, secondary. So those are 6 transformers. This is the line I told you about. How many lines here? No, not 6 conductors. How many lines? A line is 3 conductors. A, B, C. A, B, C, or maybe B, C, A, whatever the order. Sometimes they Interchange. What do we call this process?
Transposition.
Transposition. Correct. This is a distribution line. Correct. And sometimes, as you can see, what is this?
Bank, capacitor bank.
This is capacitor bank. Where is the transformer?
Single phase transformers.
Where is the single phase transformer?
Each boxes are there.
So those are those banks or transformers?
Transformers.
Okay, those are transformers. And then you pull one cable and you have this light on. Get it? So this is 3-phase. You get single phase. So this one goes maybe to 3 houses. This maybe goes to small village. Okay? So 3-phase voltage source. If you don't have a split or service transformer, they have to serve a 3-phase load. What are examples of 3-phase loads?
Elevators.
Elevators,
There is 3-phase motors in there.
motors. Mainly motors are 3-phase. And what other thing? Shunt reactors. We call them synchronous condensers. Sometimes we operate them as loads. What else?
Mainly the motors are 3-phase.
Mainly machines. Mainly machines, 3-phase. Okay? So if you go to and we have the fans in the house, is it 3-phase or single phase? Single phase. Single phase. Okay? So why do we use a 3-phase system? For these reasons. 3-phase systems produce rotating magnetic field. Magnetic field RMF is rotating. 3-phase motors can start without the need of extra equipment. The single-phase motors, they need a capacitor to start it. But the 3-phase motors can start by themselves. For the same physical size, a 3-phase generator produces more power than single-phase. Makes sense. 3-phase lines transmit more power than single-phase lines. 3-phase lines are more reliable. Think of it, if you lose one of the phases, you still have the 2 phases delivering power in your grid. So this is a visualization of a 3-phase system. Why they come in 3-phase? In the synchronous generator, we space the windings of A, windings of B, the coils, by geometric 120 degrees. Because of this space 120 degrees, the peak, once this rotor goes here, the peak is here, it's not the peak here and there. If it's peaking at C, it's maybe 0 in A and maybe halfway in B. For example, the peak of A is probably mid of halfway of negative B and C. The peak in B is negative mid halfway of the other 2 phases, etc. And what is the distance between each peak? 120 degrees. What's in radians?
5 by 180.
No, 120 degrees in radians. 2 pi over 3. 2 pi over 3. Remember, it's good to go basic level so we catch up knowledge. It's very important. We don't want to jump ahead to the pairing and then you don't know what is 3-phase. It's okay. It's the first course in the grad school. It's the toughest course, I promise. Just kidding. I think this is one of the easiest courses. What do they say in the group? What's up, group? The course. They say it's easier. Huh? It's easy. So make sure to know these questions. When they ask you for an interview, you have to make sure why 120 degrees, because in the synchronous machine, the geometric spacing between the coils is 120 degrees. That's the proper answer. Okay? Now, how do we represent them mathematically? We represent VA as VM, where M stands for max. Another way of doing it, which is the way I did it last time, what did I call it? I call it VA of T, square root of 2, VRMS, sine, I love 2 pi 60, I don't like omega. Do you remember I called it this time? So, V peak, actually square root of 2 VRMS. And for phase A, for phase B, for phase C, the only difference is they are minus 120 degrees phase shift. It means if it's t is 0, put 0 here. What sign of minus 120? It's a negative number. Multiply it by the peak, then you will reach to this number. Same for put times 0, you will find it here. Clear? This is trigonometry. It's very important. That's why they teach you in the middle school. Clear? So there is a very important concept. What do we mean by balanced three-phase system? I think we talked about it last time. Same amplitude, same frequency, and the phase shift is exactly 120 degrees. You have to know this, okay? It is very easy. For those who don't know this information, it is completely natural. Okay? So don't go and drop the course because you don't know three-phase. It's wrong. We are here to learn. As a matter of fact, probably you don't need to take the course. You don't need it. But you have to take it, but it is what it is. So we got a TA. We got a TA, and this TA will help you answering some questions, the homework. We'll probably cover some of the lectures when I'm not here. So we got a TA. That's a very good news. This is my way to represent information. This is how to convert it from time domain to phasor domain. Did we cover it?
Not yet. No.
Right, we covered it. First lecture. Anyway, basically, what is the information here that is fixed?
Amplitude. Maximum amplitude.
VRMS and phase shift. That's how can you distinguish between A, B, and C. Okay? So this is the phasor domain. This is the time domain. So the time domain, it looks like a sinusoidal. In the phasor domain, it's a rotating vector. So this would start at time 0. It would start here. And it would rotate 60 times in 1 second. If you represent it in what? If you represent it in? If you represent it in phasor domain. This is the real, this is the imaginary. Okay? So as you can see, sinusoidal. And what is this sign? It's the projection across the x-axis. The sign is what? It's the projection across the x-axis. If you project the x-axis here, look at it. You see it? And this is a rotating phasor. What's the speed? 2 pi f. 2 pi f. 2 pi 60 radians per second. Okay? Or it makes 60 full rotations in 1 second. And it makes 1 full rotation in 1 over 60 seconds. Get it? Think with me. This is the vector. Okay? I have a vector here that has a length of VRMS square root of 2. No, not square root of 2, just without square root of 2. And this is the angle here. This angle is not fixed in time. At time 0, it will begin here. At a certain time 1, it will be somewhere here. And it rotates across the time. All of them, the A and the B and the C, they would rotate, but they have a spacing. So this is only one phase, A. If you include the 3 phases, you will have 3 of these, one blue, one red, one yellow, and they are all rotate in how many seconds? In 1 over 60 seconds, they make 1 full rotation because it's 60 hertz. 60 hertz means 60 rotations in 1 second. So it takes 1 over 60 to make 1 full cycle. This is not important, but this is for visualization. And the machines people, they care more about because of the rotating magnetic field. We also have what we call the phase sequence. Usually it's A, B, C. If you flip C and B, this is what we call the negative sequence. Some circuits, they are a negative sequence, but most of the circuits are positive sequence. Have you ever seen negative sequence connection? No? In some applications they use it. Basically, to do negative sequence, delete this B, put it C, delete this C, put it B. So the B will be minus, the C will be minus 120, the C will be what? Minus 2. Okay? The Y to delta connection. Who is not familiar with Y to delta connection? Raise your hand. I want to see. Who else? Okay. So, the difference between delta and Y connection is you can see this is A, this is B, this is C. You either make a connection wire where, for example, you combine, I can't draw, you combine those legs, okay, and then you make this, isn't it? No. Where's the eraser? Anyway, the connection here is if A and B and C, you make them a common node
Yes.
and you take extension outside. Take extension outside. And then you connect your load outside.
One point is common.
One point is common, that's what we call a Y connection. It looks like a Y. Or we call it a star connection. The delta connection is the negative terminal of each is connected to the positive terminal of each. So if maybe here you connect this to that, I cannot draw. It's not easy. Because every time, the only thing is maybe we use this annotation. So how to make this connection? The positive here goes to the negative here. I cannot draw. Keeps showing. Anyway, the delta connection, you connect them as a triangle. The positive is connected to the other, and then you, from every junction you take a cable outside. One major advantage of delta connection, it blocks what?
Harmonic.
The harmonics. It blocks the harmonics. Harmonics are 120 hertz, 180 hertz, multiple of 60 hertz. Then there is the Y connection. So looking back at the stator winding figure, we see two ends of each coil. Depending on how you connect them, you either have Y or delta. Most of the time, we connect generators at, so we have a transformer. The generator side is
Why connect?
delta.
Delta.
Delta. And the transmission line is
Delta.
Y.
So,
Isn't it?
no. What we have in power plant is generator side is Y, and then the transmission side is
In generator, you also have to put hard
Yes.
for protection.
It is called
Device.
neutral ground.
Now, this is not a generalization, but in terms of the most of the problems, we connect the delta to the generator, and transmission line side of the transformer is Y in most of the problem. But in real life, it depends. Sometimes you have delta to delta, sometimes you have Y to Y. It depends. Okay, but for the sake of solving problems, you might see mixture between delta and Y. Okay?
Which is,
Yes, please.
how can we know the polarity of the inductive physically with the positive and the negative?
Well, inductor doesn't have a polarity. It's sometimes if you apply the sinusoidal, if it's the positive there, then it depends on how you apply the voltage on it. Inductors do not have, windings do not have polarity. Same for capacitors used in AC circuit, they don't have polarity. Only capacitors used for DC circuit, they have polarity. Get it? Any question? So this is how we connect the the Y connection. The ends of three phases are connected. Each one is, you extend the cable outside. And then here is the thing. We measure this voltage. What is this voltage?
Phase voltage.
Phase voltage. And it's usually denoted by V theta angle 0. VBN will be V theta angle minus 120. And VCN will be V theta angle minus 240. Now here is the thing. I want you to pull a calculator. What is this voltage? It is VAN minus VBN. So let's do it. Let's call V theta equal to be 110. Okay, volts. What is VAN minus VBN? Well, let's use the calculator. So using a calculator, do you know how to do it using this calculator? Shift to 110. Shift, there is an angle symbol. Did you find the angle symbol? If you need help, let me know. Minus 0. So I put the angle 0 degrees. Minus 110 angle minus 120. So what is the answer? The answer is 191 angle 30. Who did not find this number by the calculator? If you substitute, you didn't find it? You don't know how to do it? So go shift 2. So now you're in complex. 110 angle. Oh, I have bad news for you. 110 angle 0 minus 110 angle minus 120. Shift 2, number 3. Okay, who needs help? Quickly. No. First of all, you need to change the brightness. It's too dark. You have to go shift setup. 5 display. No. Shift setup. Contrast. Let's make it a little bit light. Split. What else we need? Shift 2. You have to put shift 2. Wait. Shift 2. No. Mode 2. Mode 2. Mode 2. So now you are complex. 110 angle 0 minus 110 angle what? Told you. VBN minus 120. And this is the answer. Shift. Oh, yes. It's in radians. So we have to change it to degrees. Mode. No, shift. Shift mode. It's in number 3. 110 angle 0 minus 110 angle minus 120. Put this answer. Shift 2, number 3. This is the final. You know how to do it? Shift 2, 3. Shift 2, 3. Shift 2, 3. Always. Okay? Who didn't do it? You will have to do it in the exam. We will ask questions. So no need to memorize this line-to-line voltage, which is basically VAB is square root of 3 VAN, add an angle 30 degrees. Because I can derive it manually. Sometimes you ask about VCN. Sometimes you ask about VCA. Get it? Get it? Let's continue. Math is hard. I just did the math in front of you. But what will happen to the line current? Isn't that the phase current same as the line current?
Yes.
هذا اسمه line. This is called line. This is called phase side. So if I draw a line here, this is the phase, this is the line, all the way to the load. So for Y connection, phase current is same as line current. And this is basically vector diagram. Take the VBN, subtract it, means you put it this way. We can move it here. If you add them, you will have VAB. It's very important. This is very crucial. Most of power engineers don't know these information. These are the basic information. What's the angle between phase voltage and line-to-line voltage? 30. Same for VCA, VBC. You don't need to calculate them. You just add 120 here. You add another 120 this side. You can get BC and CA. Example. For 120 degrees, VA is 120 angle 0. VB is 120 angle minus 20. VAB, you subtract both of them, then you should get that number. VBC, do you need to repeat calculation? No. Subtract 120, that's minus 90. Subtract 240, that's minus 210. I want you to know how to do this example at home. Unless otherwise specified, positive sequence. What time is our break? At 40. Oh, we still get 15 minutes. What's half of 90? 45. How many hours is it? How many minutes is it? 75? What's half 75?
37.
So let's take a break at 37.5 in IW. What's your name?
Rashid.
Rashid, Mr. Rashid. Okay? Remind me, please, so we take the break halfway. Loads in facilities such as building, factory, and others may be also arranged in either Y or delta. So maybe this is load A, load B, load C. Maybe we connect them. So this is Y to Y connection. So this system is referred to as what? A 3-wire system. This is wire 1, this is wire 2, this is wire 3. It's very important. Now what is happening here is sometimes we add a 4th wire where we connect the 2 neutrals together. Okay? We connect source and supplying Y connected load with 2 neutrals connected. So this is the first connection of the neutral. This is the second connection. No, this is the neutral one, this is the neutral 2, we connect them. This is usually feasible if you don't have very long distance. Okay? And what is the equation? Now because we guarantee that these neutrals have the same voltage, I can calculate this formula. IAN is what? What is this voltage? Same as this voltage. So it is like I am applying the whole VAN across ZA. So IA will be this current. VAN over ZA only for the 4-wire connection. What is the problem with the 3-wire connection? Is VAN is connected to ground and this load will connected to, we don't know. If you put the 4-wire connection, you guarantee that the load neutral same as the source neutral. And then if this is true, then this math should be easy. Ohm's law. Voltage over impedance. Voltage over impedance and voltage over impedance. Okay? So go back to the balanced three-phase system. Why we care about balanced three-phase system? Balanced three-phase system may allow us to transfer three-phase circuit into an equivalent single phase. Is this a four-wire connection or three-wire connection? Strict.
Four.
No. Four.
Pay attention.
They are the same.
Three. So they are. This is what is this symbol?
There's a ground.
Ground. What is
So
this
it's like
symbol?
one connection.
So it's like one connection. It's one of the other strategy. Ground both.
It's four wire connection.
Technically. Virtual forward. So that's why we can able to apply this set. So it simplifies the analysis. These are the requirements. But here we also add the requirement for the loads. All the loads have to be equal impedance. So basically they have to be exactly the same. If the circuit is balanced, we can use the single phase circuit and solve it. And for VBN, VCN, you just subtract 120 degrees. So this is the neutral current of a balanced load. Of a balanced load, what should be the neutral current?
Zero.
Zero. Why? Because if you add, for example, 1 angle 0, let's pretend I is 1. 1 angle 0 plus 1 angle minus 20 plus 1 angle minus 240 or plus 120. The summation should be 0. Let's do this example. A 4-wire Y connected to 3-phase. What do we have here? 120, 208. What does it mean? Is this a transformer? Is this a... Read the question. Is there any transformer in the question?
No.
No. So why is putting two values?
Is one is RMS and one is peak. We multiply with under root 3 by 120.
But RMS and peak, they are related with the square root of 2.
This is line and phase.
You got it.
Line and phase.
So 120 is phase voltage. 208 is line voltage. So if you, depending on your connection, Y or delta, depends. If you connect delta, phase voltage will be 208. If you connect Y, phase voltage should be 120. This is what we call the nameplate reading skill. Many people do not know how to read the nameplate. We're going back to the undergrad, third year. Is it third year or fourth? Third year. But that's okay. In KQB, we're here to learn. Now, is this a 4-wire? Good. So we have balance. It's connected to Y connected balanced load. So we're connecting Y to Y balanced. And the impedance per phase is 1230 degrees. So this is the value of Z. Find phase and line voltage at the load. First of all, I need to draw the circuit. Can I draw the circuit? We have to. Not cannot. We have to. From the description of this problem, we basically have VAN, Y connection, صح? VBN, VCN, and this is 4-wire. I'm gonna just put the ground here. Then we have a load, we have another load, we have another load here, put it in the ground. This is the B, this is the C. Do we have a transmission line? No. It's directly source to load. What's the impedance? 12 angle 30. What is ZB? No, not the same.
Minus.
So,
Plus 150.
minus 90.
You see,
It's set.
We do not add 120. What's the balance condition? All loads are three-phase with equal impedance. Equal means equal in magnitude, equal in angle. So this is 1230. Get it? What's the unit? Ohm. 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 Go back to the sources. What is? This is Y. So we use 120. What is this? BN. Minus 120. Volt. Volt. 120. So I can calculate now phase voltages at the load, because this is phase voltage here is the same, 120. If I want to use the line, I use the equation multiplied by square root of 3 at 30 degrees. So this is the solution. The phase voltages are the same, but the line voltages are multiplied by square root of 3 at 30 degrees. So here minus 20 plus 30, minus 240 plus 30 degrees. Okay? The second part, he's asking about the line current. How to get this line? Is the line current equal to phase current?
Yes.
Is the phase current equal to the line current? Yes, because this is Y to Y. How to get it? 120 divided by this number. Do it by a calculator. What is I phase A? Ten angle minus 30 degrees. Do it by calculator. You didn't take the break, my W. Almost there. So I'll stop the recording and we will continue after the break. Try to find the number. So when we do the line current or phase current, we do the calculations. And how are the calculations? Did you get this number? 10 angle minus 30. So for B, subtract 120. For C, subtract 240. So the delta connection in one of the phases connect to start of the another phase and they form a loop. And what do you notice? The phase voltage same as the line voltage, but the line current is not the same as the line the phase volt. The phase current is not the same as the line current. And how to get the equation? You can do KCL here, where you have to say IAB equals to IA minus ICA. And you know the relationship between IAB and ICA, so you can get IA. But without loss of generality, you can find the line current using this equation. It's this time you multiply the current by square root of 3, but to get the line current, you have to subtract minus 30 degrees. Okay? I'm not going to show you the proof, but this is you can use it. You can find IB, IC by subtract. So it's the same equation for the voltage, but you subtract minus 30 degrees. And this is the load side, where you can see the load is also delta. So for delta loads, it's the same story, and the relationship between the phase and the line current is derived as follows. You have to do KCL. What's KCL? You know KCL? Kirchhoff second current law. And then you have to apply IAB minus IC, and this is the equation. Another important thing is we have to do the load transformation. So this is very important in power system, is if you have a delta connected load, you want to convert it to Y connected to simplify the calculation. You simply use this formula. Impedance is Y, is impedance of delta divided by 3. Just divide by number 3. And here is the derivation of this. As you can see, RA is actually R1, R2 plus R2, R3 plus R3, R1 over R1. And here you can write R1 as a function of these, and if you divide these numbers, you will end up with the number 3. Okay? Question? Well, don't worry about this, okay? The better derivation is using power calculation. You have to prove that they have the same power, but no need to derive. Here we need to just apply to convert delta to y quickly. You got that? So a 3-wire Y connected 3-phase 120 208 source is connected to a delta node with the impedance per phase 1230. So can I bring it to this circuit? Yes. I divide this by 3, so it will be 4 angle 30. But here he didn't divide, so he decided to use the delta connected equation. So what do we notice? Should we pick the Y or delta? So we have to say phase and line voltages are at always 208. 0 minus 20 minus 240. Now this is easy. For part B, find the phase and the line current, they're different. So first we have to find the phase current. The phase current is actually phase voltage for delta circuit divided by the load. So it's 208 over 12 angle 30, that's 17.3 angle minus 30. So remember, we are finding what? The phase current. So we apply the same voltage across this load, Ohm's law. Now, how to find the line current? You have to use this equation. Clear? I want you to know how to solve this basic example. Note that here we have a source and load connected directly. There is no transmission line. If there is a transmission line, we have to account for voltage drop across transmission line. Okay? You have to study very good for this. I will try my best in the exam to ask questions only from the lecture. That's my goal. So whatever I say here is important. Can you do this by a calculator? Were you able to get these numbers? 208 divided by 12 angle 30 and then get IA? I want you to make sure to get your calculators right, okay? That's very important. What if I have two loads? Should we panic? No, because I can easily divide this by 3 and get 2y and find the parallel combination. So a good strategy to solve that is if I have one y, one delta, is I unify everything. I unify everything and I make them y to y. This is the first step. Convert this to what? Y. The second step is, can I find the parallel combination between the two?
Yeah.
How?
Single phase.
Single phase. So how to do it? Let's do it by hand. So I have Z1 in parallel with Z2 after converting it to Y. What does 2Y mean? It's the second load after converting it to Y. They are in parallel. How to do it? It's 1 over 4 plus J3 plus 1 over 4 minus J3, and then I take the inverse. Correct? Do it by a calculator. To do it by a calculator, I have to open parentheses. Inside this parenthesis, I put 1 over 4 plus 3 times j plus, you do it by a calculator, 1 over 4 minus 3 times j, and then I take the inverse. And then I can find the number 25 over 8. So it turned out the imaginary parts are gone after taking the parallel combination. So this is the correct answer, 25 over 8. You have to use this calculator, your grad students.
35 over 4.
What is 35? 25 over 8.
Over 4. 8.
There is no way Dr. Muhammad Khalid, Dr. Muhammad, Dr. Mahdi is wrong altogether. So No. This is a very good slide. We've been using it. We know about it. We trust it.
This is the wire forward system or CUR system.
Hmm?
CUR system or forward?
No, this is a 3-wire.
According to the phase is equal to
We assume that the neutrals are the same. Let's make it simple. So we can find the line current to be 120 over the impedance. It's 38.4 for phase A. For phase B, what? 38.4 minus 120. For phase C, 38.4 minus 240. For a balanced, so this is a summary. For balanced Y, if there is Y, you have to use this line voltage, and this one is what? Line current. This is line voltage, this is line current or delta. So this is a final summary about delta and Y, and try to read it. Note that VAB leads VA by 30 degrees for ABC sequence. In case you're doing negative sequence, you have to reverse the signs. You have the negative sign for the angles. Power. What is power? What is the title of this course? Power system. Power system steady state analysis. Lots of the time in our analysis, when we do Newton-Raphson, when we do any power flow, we do calculations in power. So it doesn't make sense, we don't understand the power calculations before jumping into numerical calculations that are applicable to power. So what was our flow of the course? I told you, power systems, they need to be stable. How to do it? You have to find information. How to find this information? You have to do power flow analysis. But wait, do we all know power? I don't think so. Do you know power? Who taught you? Doctor?
Not that one. I have many.
And power. Who else?
No idea.
Power. You took power branch?
Yes.
The major. Anybody did non-electrical engineering degree? Bachelor? Computer?
Yes.
I see. Computer is cousin of electrical engineering. So let's look at the voltage equations and current equations. So what is the instantaneous power? For phase A, I multiply VA by IA, I get the real instantaneous power. What does the instantaneous power? I multiply the instant of the voltage times the instant of current. So let's do the math. Well, math is hard. So it is 2 VI. Why we have 2? Because each one is having the square root of 2. Square root of 2 times square root of 2, we have 2 VI sine omega t times sine omega t minus theta. Repeat for B, subtract 120. For C, subtract minus 240. So we are familiar with this trigonometry. Sine alpha sine beta equal half of cosine alpha minus beta. Cosine minus cosine alpha plus beta. And if you apply this trigonometry, you will find that each term would be VI times cosine theta minus cosine twice the frequency. So what is the conclusion? The frequency in a 60 Hertz, the frequency of power is what?
60 hertz.
About
Double.
something.
It's 2 times.
That's fine.
What is 2 times 60?
120.
120 Hertz. For Pakistan,
100.
100 Hertz. This is in IW information, okay? It's very important. How many of you didn't know that the power has twice the frequency? Did not know. First time? First time? That's why we're taking this class. To make sure you in graduate school, you have the proper concept. And I am giving you a disclaimer. Anytime you make a mistake in doing your research, trust me, most of the time the mistake comes from 520. Maybe you are miscalculating frequency. Maybe when you do the calculation, you put power, I'm going to plug power, I put 60 Hertz. And then you submit a paper, and then they laugh at you. No, we don't want people to to capture simple mistakes that we can learn in this class. So never ever plot power 60 Hertz. Never ever. Power is a complicated signal. Some of it is constant. Now what do you notice about that? VI has two terms.
Yes.
One is constant number. VI cosine theta is a constant number. It's not a function of time. The other one is a function of time twice the frequency. Okay? It's very important. Now here is the catch. One smart student said, I'm going to add power of A, B, and C. If I add all of these powers, what will happen?
If we add the negative side, the pulsating terms will get cancelled.
Correct. So these terms will cancel each other because remember, if you add 1 angle 0 plus 1 angle 120, minus 120 plus 1 angle minus 240.
And that's the reason that we are using three-phase, because we have a constant power. If
We have a
are using
constant-
single-phase, we have two terms. One is
Active.
constant and one is pulsating.
Thank you. That's why we use a three-phase system. We use a three-phase system because this pulsating power will cancel each other. So what does that mean physically? It means the generator will not vibrate. It will be stable. And this would make the lifetime of the machine way longer. Generators have been running for more than 50 years. Correct? 40, 30. Some are 50 years old. There are generators that are really that old. So if you do the instantaneous power, the oscillating components cancel each other, and the constant real power is actually 3 VI cosine theta. That's how we derive this equation for real power. So the total power is independent of time. The total power is always fixed. For three-phase system, if you sum all of them, it's always fixed. Doesn't matter what time. And that's why when we have a 10 megawatt power plant, we know it's 10 megawatt because it keeps sending this at a constant rate because it's the three-phase system. This is very crucial, okay? So never ever memorize, try to understand how we derive these equations. Now here's a table. I think I made this table myself. This is the table is how to get the equation and the unit. So the total real power is the 3 V RMS IRMS cosine theta. Now how did we get the term sine? There is mathematical notations I didn't tell you, but if you expand cosine twice, you can get sine and cosine. So this term would be expanded into two other terms, sine and cosine. If you remember, cosine of 2 of alpha would equal to, I think, sine of angle minus cosine of angle, something like that. But I'm not going to show it. You can find them later in the textbook. But that's why we get the total reactive power to be sine. And if you add the total complex power, it's 3 VN I conjugate. It's actually the summation of, it's the square root of P squared plus Q squared. And sine squared plus cosine squared is 1. So it will be basically 3 V RMS IRMS. This is what we call the apparent power, which is the magnitude of P plus JQ. Okay? So do you remember in power system, probably I didn't write this equation, but complex power is P plus J times Q. And if you put the three-phase, apparent power is what? Square root of P squared plus
Q squared.
square. If you do this, if you square this, you should reach this. And of course, the other way, or the other notation, is this is a 3 VAN IA conjugate. If you do, this is two equations for the complex power. And how to do the conjugate? Shift to conjugate. Or flip the sign of the angle of the current. Or replace every J with minus J. We'll do numerical examples. But I want you to know this table. Keep these equations in your mind. However, there is theta here. What is this theta? Theta is the angle of the power factor, which is the angle of the voltage minus the angle of the current. Angle of phase voltage minus the angle of phase current. And this is the power triangle. This is the power triangle. I told you before about it. Is if you know two quantities, you can find the other two. So these equations are important. Okay. Three-phase balanced load has a phase voltage of 120. The load has an impedance per phase. So if he didn't say if it's Y or delta, what should you assume? Assume it's Y. He didn't talk, it's Y. So delta is the special case. So find the phase current, 120 divided by 1230. Divide this by that. What is the real power per phase? Real power per only one phase, you don't multiply by 3. These equations for how many phases? 3. So for one phase, you don't multiply by 3. So here we use the equation. VRMS, IRMS cosine theta. What is cosine theta? Is the angle of the voltage, which is 0, minus the angle of the current. So 0 minus 30. Okay? So that's how to get the real power. What's the real power? 1040 watt. So for 3 phase, how to get it? Multiply by 3. So what's the total real power? 3 times that. What is the total reactive power? 3 times VRMS, IRMS sine theta, where theta is what? 0 minus 30. It's a plus 10. Watch the YouTube video. Okay? And what's the total apparent power?
Total.
Use the equation without the sine or cosine. So this is a simple example that illustrates how to calculate power. Okay? And it's very important. Is it useful today's lecture? Is it useful?
Yes.
Is today's lecture useful or waste of time like the previous one? Previous one was more important. PGM, MISO, what else?
Haircuts.
ERCOT, what else? New York, what's New York? What? New York, for New York, what was it? NISO, what else we have? Quebec, where is Quebec? Quebec, what else?
ISO.
What is NISO?
ISO. California ISO.
See, these are good information. Okay, what else we have? Hmm?
SERA, SPP, ISO, RTO.
Okay, good, good. I want you to know all these amounts. Are RTUs remote terminal units?
Regional transmission.
So RTUs has two things, remote terminal units and regional transmission operations. Are you familiar with RTU?
Is it like sensor or something to portable?
Yeah, it's for instrumentation. It's remote terminal, it's junction boxes. Now here's one thing. These equations are based on phase or line quantities. Phase. So if I convert them to line quantities, what will happen? You have the square root of 3 will come into place. And the equations, if you use line quantities, you replace the 3 with square root of 3. That's the only difference. If you use line quantity instead of phase quantity, expect square root of 3. Why? Because of this equation. V theta is V line over square root of theta. So to write it as a function, the original equation, if you substitute V line with square root of V theta, you only left with 1 square root of 3 outside. Because the square root of 3 times square root of 3 is 3. So you already have a square root of 3. So you leave another square root of 3 outside. If you multiply them, you will have 3. Get it? Why it's square root of 3? Can you derive this equation? Yes or no? Are you sure? Or do you want me to do it by hand? I can do it by hand. Anybody wants me to do it by hand? Okay. So if you're using line quantity, I line or line, not phase, then you use a square root of 3. If you're using phase, you use what? 3. Get it? Get it? Okay. Same for the apparent power. Now if you have a balanced delta connected, you have to, it's the same story. It doesn't matter. Because the square root of 3 would come now from where? From the current, not from the voltage. And 3 should be replaced by? So always, am I using line or phase? Based on that, proceed with the power. What's the question? Am I using, you have to repeat it.
We are using line or phase.
Phase.
And accordingly proceed.
Accordingly, you have to. Get it? Let's do this example. 4Y, your favorite. 4Y, Y connected, 3 phase, has a line voltage connected to Y balanced load. The impedance per phase is given as 5 plus J 5 ohms. Find the total 3-phase power delivered, total reactive power, total apparent power. Let's do only the real power. How to do it? VAB is what? 173 angle 0. So because this is Y,
We need the phase voltage.
so we use the line voltage, should be multiplied by square root of 3. No, it's given here a line. So we use the square root of 3. So, but before that, do I have the current? No, I gotta get it. How to get the current? It's 100 over this impedance, 5 plus J5. This is 5 square root of 4 or 5 is 5J5. How did I know? Because if real and imaginary are the same, you should be the angle 45. So this is the line current, which is equal to phase current, 14.14. What's the angle? 45. So I know this, I know this, I know that. I can calculate the real power to be what? Square root of 3, V line, I line, cosine theta. What's theta? You get it from the current. Okay? For reactive, for apparent, we use the same equation. Any question about this example? So try to, when you go home, you have to study them. As a graduate student, don't sleep. Do them without looking at the solution. We might have questions in the test about it. So for a balanced 3-phase, what is also good thing about balance is we multiply by 3. If I get 1 power, I just multiply by 3 because all the real power for phase 1, A, B, and C, they are all the same. Even if I have a balanced, if we have 3 loads that are balanced, the first load, the second load, and the third load, if they have same impedance, means they have the same power. And this is the complex power equations. One more time, I want you to memorize them by heart. They are very important. Okay? The concept of power factor. Power factor is nothing but cosine of the angle of voltage minus the current. And depending on the real power, whether it's leading or lagging, you say it's lagging or leading. If I have inductive load, it's lagging. How do I distinguish inductive load? Let's go to the previous example. Is this inductive load or capacitive load?
If current is inductive.
It is inductive. Why? Because the imaginary part is positive. If the imaginary part is negative, that's capacitive load. If it's capacitive load, power factor is leading, not negative. There is no negative power factor. Cosine theta, power factor is always positive.
The angle will be negative.
No.
Above 1.
Yeah, the angle is negative, but the power factor is what? Positive number leading or positive number lagging. So power factor actually, as a matter of fact, is actually cosine of that angle. But what's cosine of that? Cosine of an angle is the adjacent over the hypothesis. P over S. مجاور على الوتر. Get it? So the real power performs real work, transfer real energy. Power system components are rated usually by apparent power. I told you, when you open your power plant, you don't say it's 5 plus 5J megawatt. You say the apparent power. So usually they are rated by the apparent power. And the power factor measures the consumption efficiency. How efficient our utilization for the apparent power. The closer to 1, the better. Closer to 1, the better.
And the half is like let's
No, anything below 0.85 is horrible. Half is way too low. In your power operation, if you're below 90, you're bad. 85, you're really bad. 75, shut down the business. Clear? So never ever operate at a power factor that's below 0.8, 0.75. That's usually industrial application, they always operate at low power factor. So how to calculate this equation? So note that it has to do with the type of load, if it's inductive, lagging, if capacitive, leading. And one other thing to know is Q is 0 for unity power factor. Q is positive for inductive and negative for capacitive. It supplies. Positive means absorb. And this is how we change them in curve. That's not important for today's lecture. Let's do this example. If the line voltage is balanced, Y connected load is 208, total average power is 900, power factor is 0.8. Determine each load. So you have to find what? Z.
Can we do it in next times?
Well, we took the 5-minute break.
Yes, it's 21.
Still have 1 minute. Still 9:50. This was agreement. Do you want to change the agreement?
Come on, guys.
Is
It's
it
up to you. We can finish at 9:25, but no break. One more. Time is over. We will do this example. Okay? 9:30. Okay? No, that's the rule. Okay? We're professional.